Now we're getting to some of the fun stuff. Challenge number 1, part 1. On occasion, we will create a practical application using the instructions that we have discussed in the manual. This is the first of these quasi-practical applications. Everyone can conceive of a conveyor belt. Basically, in a sense, it's two pulleys with a belt going between the two pulleys, and one of the pulleys is powered by a motor and the other one is an idler pulley. It just so happens that they're more like rollers because they're long and they don't necessarily have grooves in them, and the belt that goes between them is very wide, very broad, and things travel on these conveyors. Everyone can picture a conveyor. In the lab manual, roughly on page 160, 161, something like that, is challenge number 1, part 1, and there is a graphic showing 3 conveyors. Each conveyor also has a motor conveyor 1, motor conveyor 2, motor conveyor 3. And the conveyors they're labeled 1 conveyor, 2 conveyor, 3 conveyor. There's also 4 photo eyes labeled 1 PE, 2 PE, 3 PE, 4 PE. These happen to be reflective. It shows a reflector on the opposite side of the conveyor from the box marked as the photo eye. This type of a photo eye has a transmitter and a receiver, and it's designed in such a way that extraneous light does not affect it. We also introduced you to something called a functional specification. Those of us that write programs affectionately refer to it as the funky spec. Usually because it's funky. It's not always complete, might have some poor grammar in it. Nonetheless, in most cases out there, you're going to be given a functional specification, or you're going to have to interview the mechanical designer, the machine builder, or the customer or customer, and you're going to have to write up a functional specification based on what they tell you and what you see, and then you're going to hand that to the customer. They're going to read it and say, yes, that's it, or they're going to say, no, that's not it, and here's why. And you will keep massaging that document until the functional specification is what both you and the customer agree on. This is what you're developing the control system for, and you're going to program it to do these things. Our functional specification is funky. It's not real perfect, but there's enough there to get you started. 3 belt conveyors, each with a motor driving the belt. We want a start and a stop push button for each conveyor. With an interruption in program execution or power, we do not want the conveyors to continue running if we leave the run mode and return to the run mode, whether it's because of a power cycle or a mode cycle. Considering the lab that we just did and just discussed, you already are getting ideas. We want a system start and a system stop push button. That could sound like one push button, but we want a system start push button and a system stop push button that enables the conveyors to run, enable only, not run, enables them to run, or disables them from running. This does not actually start and stop the conveyors directly, just enables or disables their ability to start. Following a system stop, we do not want the conveyors to be running with a subsequent system start, regardless of their state when the system stop occurred. Each conveyor will have a unique rung of logic to start and stop them if the system is enabled. More grammatically correct is each conveyor will have a unique rung of logic to start and stop them. The logic within that rung will allow them to start if the system is enabled as part of the logic. Okay, now in the manual it says don't turn the page unless you want to see the solution that we are providing before you have exhausted your own imagination. You might use the existing tags for 1M and 2M, but I would create new ones to exercise that skill set. You may want to delete your existing logic and tags before starting. I will delete the logic, but not the tags, as you will see later in this manual. We will not integrate the photoelectric eyes until much later in the manual. Depending upon whether or not you have switches wired to an input module card, and how many switches are wired to the input module or card, you may have to use program tags defined as booleans, but not aliased to an actual member of a module-defined data type, meaning you may have to have start push buttons that are tag names, but they aren't aliased to an actual input because you don't have any inputs or you don't have enough. We will do both this time only, and in the future you will remember the procedure and you could decide for yourself how you want to use your limited I/O, your limited module-defined data types. Be sure to save your existing project as previously named, and then save the new one as beginner L, whatever your processor number is, Challenge01 section 1, or step 1 if you like, S1. You are more than welcome to use your own abbreviated version control, but make it clear enough to be able to look for a project file 60 days from now and be able to find it. Beginner L31 Challenge 1, this is the first challenge. You can just call it 01 if you want. I put S1 in front of it. Okay, now next we're going to discuss the solution. I told you that you are better off starting from scratch, more or less. Create a new project, add your I/O cards, and create new tags. But I'm going to start right with what I have because I'm lazy. No, I'm not lazy. I just don't want to spend the time. So I'm online. So first thing I need to do is to go offline. Now I've already saved this, so I can just go offline. Now with RSLogix 500 MicroStarter Lite, if you use those development software packages, when you went offline or you did something where you should have saved it, it would almost always ask you if you wanted to save it. RSLogix 5000 does not ask you if you want to save. I just went from online to offline and it didn't give me a peep. I'm going to select rung 0, delete, delete. Now I have one rung here. And in the lab manual, and I'm going to, by the way, flip this around a little bit. In the manual, we've got the stop push button here where you would normally expect to see it in an electrical circuit. Normally, if this were an electrical circuit and this was a relay coil, and this was a contact associated with that coil, the start and seal in would be first and then the stop second. It really doesn't matter whether this contact is here or over here. It's in series. It's going to behave the same way. But just to give it a more conventional look and match the manual, I'm going to go up here and I'm going to type in start conveyor 1 push button. And of course, there's no tag by that name. When I click away from it, we have an undefined tag. And I'm going to drag this over here to this tag Mimi, and I'm going to go in and change the ART to OP. Again, we have an undefined tag. Then this I'm going to call motor conveyor 1. So MTR. And again, that's an undefined tag, and I'm going to drag that undefined tag over to this tag Mimi. Now, everything you see here is undefined. Okay? And at this point, I'm going to go to Program Tags, and I'm going to delete all of these. If I go to Controller Tags, there's nothing there but our module-defined tags, which is good. We don't alias them yet. The solution. Start and stop of a single conveyor with an undefined descriptive tag. I moved the stop instruction to emphasize the indifference to the location of that function before or after the start or logic. I have an abundance of I/O, but I did not alias the module-defined tags to demonstrate a key feature of RSLogix 5000, which is that of concurrent engineering. This feature, referred to as concurrent engineering, allows you to write your entire program without knowing the installed I/O configuration. So you see down there we do have an installed I/O configuration. We have a 1769 IQ6 XOW4. Gives us 6 inputs and 4 outputs. However, if you had a functional specification, which you do in the manual, without any I/O configuration, you can start writing the program. You can give all of your inputs and outputs tag names that make sense to you, and later you can alias those tags to the module-defined tags of your choice after the I/O has been configured. This also reduces something called data scattering, which is the result of placing the I/O of a single process section in more than one contiguous location. Meaning when you first started with your, actually if you were aliasing these push buttons right now to actual I/O input points that are going to be wired to actual field input devices, push buttons, and you went through the whole process, let's say you had 15 conveyors. And so you wanted to keep everything for conveyor 1 in one location, contiguous tags, etc. Let's say you get all the way done, you've got it all assigned, and then you're working with it, you go, oh, I forgot something. You forgot one tag for each of the 15 conveyors. Well, if you've made them contiguous, meaning you didn't leave any space in between the I/O points, then you have no place to put them. What we mean by data scattering is, for troubleshooting purposes and programming purposes, it's good if all of the inputs associated with that conveyor, conveyor 1, are all on the same module in sequence, and they're contiguous, meaning that there's no gaps in between them. That's what we mean by preventing data scattering. It is even better if you write the bulk of your program before I/O assignments, thus allowing the most logical, contiguous I/O assignment possible. This feature, concurrent engineering, also allows you to discover additionally needed I/O devices that would not be apparent until the program is written and you discover that you do not have the device on the I/O sheets of the drawing set. In other words, if you wait until the drawing set is complete and then you sit down and you go in and you create all your tags, alias them, you look at the descriptions on each I/O device, and then you alias it to that module-defined tag, then start writing your program. And as you're writing the program, you realize that you need a photo eye on a particular conveyor, and it needs to go in a particular spot on a particular I/O card. If you wait until the drawing set is complete, everything is assigned. They're not going to go back and start shifting things around to add another photo eye in the best spot for it in the drawing set. Instead, they will add it to another I/O card that might be 10-15 sheets away. Now, it'll still work. That's still fine. That happens all the time. But it would be much better if before the I/O was even assigned, meaning before the I/O sheets were even drawn, that you gave a list of the I/O needed to whoever is actually drawing up the design of the control system, drawing the configuration for the I/O, to show them what you need and let them then follow your list. What we're suggesting is that the dog wag the tail, not the tail wag the dog. And I'm sure people who design control systems feel they're the dog and the people that program, they're the tail. However, whatever the designer does, the programmer is stuck with it. So do yourself a favor, get used to using concurrent engineering, writing your programs without using the I/O assignment. If that is, it's not already done. If it's already done, well, then you're stuck with it somewhat. Either way, you're better off writing your program without assigning I/O and then go back and alias it to actual I/O. Either way, it's going to work out better for you. Also, we define these as program scope tags. Well, these are undefined yet. I haven't defined them yet. But I'm going to define these as program scoped tags. See, if you know everything's properly selected, you're done. You just right click, new, create. Right click, new, create. These are all program scope tags. The reason you want to do that is because later on you may want to create another program for another section of the distribution center where these conveyors are. Let's say you have 7 bays. That would be 7 large areas separated by walls that have a material handling system, and they're all identical. And you have semis that come in and unload 700 Blu-ray players, and then they're distributed through the material handling system to 10 doors on the other side of that area where trucks are loaded up to go to individual retail outlets. And the Blu-ray players, by way of the connected enterprise computer that tells the PLC how many to divert to each distribution truck. You got a picture of what could be done in that one area. Well, let's say you have 7 of those. Why should you have to write and create unique tags for duplicate programming and duplicate code instead of just writing it once like we're doing here? Then once it works, then you create another program with another program tag database, and you copy and paste that from this program into the other program. Remember, I said that the program tag databases are isolated from each other. These 3 tags you see in front of you, start, stop, and motor, conveyor 1, push button, and motor, these can be used again in other programs. Now, the only difference is that they're going to be aliased to different I/O, because if you have one large controller, chances are you'll have a separate controller for each distribution area. It is not hard to justify using a separate controller with distributed I/O in each of these 7 distribution areas in this big distribution center. The cost for an additional processor and power supply pales in comparison to the money saved in design time and maintenance and troubleshooting and downtime if you have a separate controller and all 7 controllers start out with 100% identical programs. Or you can put it in one big controller and then just have multiple programs. So you have that option. Personally, I would use many smaller controllers instead of one big one, mainly because if something goes down in one area, you don't have to shut down all 7 areas because you only have one controller. With 7 controllers, you just shut down the area where you have the problem. Okay, moving ahead. That's why we put these in program tags instead of controller tags, in case we want to reuse them. Now, if we don't reuse them, they work fine in program tags or controller tags. Your logic will look in both locations for the tag. However, all I/O tags or module-defined tags, they always go in the controller tags. There's no choice. You cannot put them in the program tags, it won't let you. Okay, if you want to test this running logic, save as Challenge01, which we did not. So I'm going to go up here and save as Challenge01. I'll put a 00 after it, just so I know it's the first version. Download and go online in the run mode. We're downloaded and in the run mode. All bits should be off. If you have any outputs that are still on, they got left on by the previous program, go to controller tags, go to monitor tags, expand the output, and these should all be off. If they're not, click on them, type in a 0. Here's our code. This will be a rare demonstration of testing your code without I/O or module-defined data types by toggling the bits from your keyboard. We've already done this somewhat. Let's toggle on the stop bit first because that would be on. Okay, shows it highlighted. That would be on because it's a normally closed push button. Because the stop conveyor 1 push button is a momentary push button whose normally closed contact completes the input circuitry or logic, this bit would be in the on state when the system is at rest, no push buttons pressed. If you do not understand this logic, a true if on instruction examining the bit in memory whose state is controlled by a normally closed stop push button, then you need to revisit the earlier video lectures on Introduction to PLCs. This simulates pressing and holding down the normally open contacts of a momentary push button. So in this case, if we had a normally closed push button connected to an input, an I/O module, an input module, if that button's not pushed, then that input is on. And if you're examining it with this tag, then this would be on. We're not alias now to any I/O, so we had to toggle this on to simulate that condition. Then we had to go here and simulate toggling or pushing this button on, and you see that becomes true. It turns this bit on and this bit is now on, and then toggle it again to simulate releasing the push button. That was what it meant by this simulates pressing and holding down the normally open contacts of a momentary push button. That's just what we just did. The operator has the momentary push button depressed and will next release it. And so we showed you that. We did both toggles. Okay, we went the distance in the manual. We didn't skip any steps. Just in case you have forgotten, toggle bit flips the state once with each execution from off to on or from on to off, both of which you just did. 2 toggles equal the operator pressing and releasing the push button. The operator has now released the spring-loaded momentary push button, and the conveyor motor is energized and the belt is moving in a forward direction, transporting whatever or nothing that is riding on the belt. Then we had you stop the conveyor by right-clicking, toggle bit, see everything's off. Now because that's a push button, we right-click again, toggle again. That just simulated pushing it, which turns it off, stop the conveyor, releasing it, and now that instruction is true again, waiting for you to start the conveyor again. That simulated pressing, turning off the normally closed contacts and releasing, turning it back on. This leaves the rung of logic in the state of rest. Normally open buttons off and normally closed buttons on. Okay, that concludes the testing of your logic online in the run mode without the benefit of real I/O. Save and go offline for the next edits. We didn't really change anything, so I'm just going, we don't have to save it because we haven't changed anything, but I'll save it anyway. I'm always telling you to save it. Okay, it's saved. Now the customer has requested 3 conveyors that operate like this one. And I show you a little shortcut, and basically I selected this conveyor and went Control C and then went Control V twice, just like you would with a word processor. Now here's where you can very easily get yourself into a jam. If you were to start editing these tag names, okay, if you right click, edit, and you change that to a 2, you're making a big mistake. I'm going to go do that anyway, just so you can see what happens. Now we're editing conveyor 2 here, right? The second rung. Watch what happens. Apply. That did change it to conveyor 2 push button, didn't it? Oh, looky up here. It also changed it up there. We edited the tag. We didn't create a new one. So now we no longer even have start conveyor 1. It's no longer a tag because we edited it. We changed it from conveyor 1 to conveyor 2. That other tag doesn't even exist. See, if we go up here and right click, see, we can't. Well, let's put that in the edit mode. Change that to a 1 to get the other tag. Now I know right away it's not because this didn't reverse video showing white text with a blue background. So we'll hit enter. Look, that's now an undefined tag because we edited what was conveyor 1 to be conveyor 2. So we'll go create that one again to get us back where we were at. And this rung doesn't need to be in the edit mode. Okay, now that's back the way it was. And these are the two that we needed to change. So we did edit a tag, and it changed all the start 1 conveyor. So this down here says 2 also. So it looks like we're digging a hole, but we're not. Just make sure that you pay attention whether you're creating a new tag or editing an existing. Just to knock the confusion out, if there was any, we'll go back to where we were at, right there. We will also go to Program Tags, and we will delete this tag. Well, we have to go to Edit Tags to do the delete. Now we're back to where we started. Click on that one, Control C, Control V, Control V. Now we'll double click here. We'll make that a 2. Double click here. We'll make that a 2. Double click here. We'll make this a 2. Then we'll drag this one down to here. Double click here. Make that a 3. Double click here. Make that a 3. Double click here. Make that a 3. Drag this one over to here. Now, these aren't tags. We haven't created any new tags. All we've done is throw some text in the tag field for these instructions, but they're not tags yet. However, right click, start new, make sure that's main program and hit create. So right click, new, create, right click, new, create. Now we're online, so see we still have I there for insert. Right click, new, create, right click, new, create, right click, new, create. Now we can do finalize all edits. And we're done. And we can right click to toggle these stop buttons to show the state they're supposed to be in. And then we could go do the start buttons and turn on 3 separate conveyors. Now this is all internal tags. These are tags that we created. They're not aliased to any I/O, and at this point you can't alias them to I/O while you're in the run mode. So if we go to edit, see that's grayed out. You cannot change the type once you create it. That's why I'm telling you, if you make a mistake doing this online, you have to go offline to fix it. So just to demonstrate that, so you know I'm not fibbing, we'll save it first as part 2 or version 2 because we made some changes. Version 1 was before we added conveyor 2 and conveyor 3. Now let's go offline and right click. See, now you can change the type. You can alias it. You can't do that online. A reminder, I just changed the 1 to a 2 in rung number 1 and the 1 to a 3 in rung number 2. Do not open the properties and edit the tag names. That will change your existing tags, not create the new ones that you need. And I'm telling you, even after you've done this a lot, you can still make that mistake. Oh, what a mess that makes. If you've got a big program and you've used a tag in, say, 10 different routines, and you accidentally edit it as part of other code and you don't notice it right away. Oh my goodness, what a mess. Be very careful when you're messing around with tag names that you're conscious whether you're editing an existing tag because you want to give it a different name, not a new name, a different name. If you're working with a new tag, do not open the properties on an existing tag. Just type it in, then right-click, new, change whatever, and create. Now, once you become confident in what you're doing, you can double-click on the tag name, edit the characters, press enter. Right-click on the undefined tag name, select new, and after making sure the tag scope is correct on the first line, then select create. This can be done in seconds, but only if you are confident in what you are doing. We know that these individual rungs of logic will work for each conveyor because we tested it on Conveyor 1, and we have unique tags for each conveyor. We also were requested by the customer to give them a system start or enable and a system stop disable functionality. We're going to do that next. We're going to create one more rung. I'll just click on this one, Control C, Control V. So now I have two rungs alike. We want to put this new one on top. We will call this, see, I double click, I'm going to change the name. And it's 6 1/2 dozen of the other, which is easier. I'm going to drag it over here. And then double click, drag my mouse through ART and put in OP. And then over here, I'll just double click, System. And you don't need a space, you can just go with enabled. And the rule of thumb that I use, if I can easily see the uppercase letter as a delimiter on those two words, then I leave it like that. In some cases, it doesn't show up real well, like if you have a lowercase l followed by an uppercase I, it looks like two lowercase l's or two i's. Then you want to use an underscore. In this case, this is good enough. This then gets drugged down to here, and there your rung is finished. But none of these are tags. Define these tags as program scoped. Right-click, New, Program Scoped, Create. New, Create, New, Create. Notice that the logic is identical. We're not going to download yet. Another thing with your new rung, this gives you a bit that the operator can energize and de-energize as an indication to the controller that the conveyors are enabled to run or shut down and not enabled to start. But what do we do with this bit and the other three rungs to effect or cause that functionality? You guessed it. We go to the beginning of each rung and put in a true if off. We drag over system enabled. Now there's many ways you can do this. You can repeat what I just did 2 more times, or you can right click, copy, click there to bring the focus there, Control V, select, Control V. Okay, now if the operator, and by the way, this would be turned on, so we'll toggle that. Now we're not online right now, but we do have an offline database. I just toggled the bit on in the offline database so this would look right. So right now all the stop buttons show that they're on. So if we right click here, toggle on, if we were in the run mode, we did that, this would be true, that would turn on, and this would be true, and all these would turn on. We'll save that and we'll do that again. We're offline right now, so it really doesn't work. We will probably not have you exercise your logic by toggling bits in the memory again after this instance. Since we do not have our tags aliased to field devices, I/O that is, we will exercise our logic by toggling memory locations. I am going to have you download it. One thing I will point out, when we are in one of these challenges or sneak peeks, especially the challenges. We're not going to give you a step-by-step. We want you to kind of think this through for yourself. And if you make mistakes, that's fine. If you come to a point you realize you should be online and you're not, well then go online. Obviously, on page 166, 167, whatever it is, it says this enables the system and leaves all the conveyors in the on state. Toggle any one. Well, you can't toggle it, not really, unless it's in the run mode. Let's go ahead and toggle this one. You see now that bit came on, so we're going to let go of that push button. We pushed it, now we release it. This stays on. System enabled, and all of these are enabled. So if I were to start conveyor 2 by toggling it on, toggle it back off, conveyor 2 is running. Okay? That's how we want it to behave. If someone hits the stop system push button, watch what happens. I'll toggle that back on like releasing the button. Not only did it drop out system enabled, it dropped out any conveyors that were running. So that's one of the first couple points of the functional specification that we wanted. So in the manual it says toggle any one of the stop conveyor push buttons off and back on. Now first though, we had you start all the motors. Well, to do that, if we do start, if you push the start push button, nothing happens because the system's not enabled. Okay, so we'll enable the system. Now I'm going to cheat. Instead of toggling this on and off, I'm just going to toggle this on. Okay, and instead of doing all these buttons on and back off, I'm going to cheat. I'm going to toggle that on, and toggle that on. Shame on me, I cheated. But it ends up matching what's at the top of page there on 166, 167. And so then I show you there 1, 2, 3, 4, 5, 6, 7, 8 steps. 1 and 2 is toggle system start on and off. 3, 4, toggle start conveyor 1 push button on and off. Same thing with start conveyor 2 push button, start conveyor 3 push button. And then right next to it you see that the system's enabled, all the conveyors are running. Toggle any one of the stop conveyor push buttons off and back on. So we'll do this one. We'll go off and back on. Did it affect any of the other conveyors? No. Toggle the system stop off and back on. Did any of the conveyors stop? Yes. How many conveyors stopped? All of them. Did any return to the on state when you toggled the stop system off? Well, of course not. That's almost a silly question. Now, toggle the start system push button on and off. So, toggle it on, toggle it off. So now we have our system enabled again. Did any of the conveyors return to the on state? No. Why? Because we have to restart them individually from these start push buttons. The system enabled does not start conveyors, but it can stop them, but it can't restart them. That's pretty simple right there. I think you can all picture that, in your mind. And remember, somewhere in the lectures I talk about being able to visualize. If you cannot visualize 3 conveyors, everyone's seen a conveyor. If you can't visualize 3 conveyors in sequence, so what's on conveyor 1, if it keeps moving and hits conveyor 2, if conveyor 2 is running, then it moves on to conveyor 2 and it gets to the end of conveyor 2 and hits the entrance of conveyor 3. If conveyor 3 is running, then it pulls it on to conveyor 3, gets to the end of conveyor 3 and goes on the floor or wherever. If you can't picture that in your mind and picture this logic in front of you, you need to back up and keep working at it until you can visualize in your mind, with your eyes closed or open, the conveyor system. I suppose if you have to close your eyes to visualize it, that's okay to begin with. But you ought to be able to visualize any of this with your eyes wide open, looking at almost anything else. We're done with Challenge 1 Part 1. So save. See up here it says, well, it says 2. So save is 3. Up here, see it says Challenge01, 02, File, Save As. Now, if you didn't make any changes between what you saved as 2 and what you saved as 3, what difference does it make? If you go back and look at 2 and it's what 3 is, you've got what you want. If you go to 3 and don't go to 2, you still got what you want. Save more often and just keep giving it sequential names so you can always go back to where you're at.